Also in section 2, we need to talk about the washer method for finding volumes. So just to kind of review what we talked about previously, the disk method is when whatever slice we were looking at, that representative rectangle, it was perpendicular to the axis of revolution. And so an example of the disk method is find the volume of the solid formed by revolving square root of x equals 1, and y equals 0 about the x-axis. So sketch first. Here's the square root of x graph. If I cut it off at x equals 1, I'm at the point 1, 1. That y equals 0 just means we're looking at this section. Rotate this around the x-axis so you get this little kind of shape going. Kind of like to dot this one like that. So you get this kind of thing going, but what you're really looking at is, okay, so what is that representative rectangle? What is r? R is the distance between the curve and the axis of revolution, which is simply square root of x, technically minus 0. You don't have to write that. So the volume would be pi times the integral. In terms of x, we're going from 0 to 1 of square root of x squared dx. All right, so we can integrate that. I'm not going to. It's going to be something like pi over 2, but again, that's not the point. To have more time to do the washer method, I want to get through these examples. Find the volume of the solid formed by revolving square root of x, y equals 1, and x equals 0 about the y-axis. Okay, so here's square root of x again. But remember, that's the square root of x graph, yes, but we want it in terms of x when we're integrating. So it's the same as x equals y squared, but just part of it. Y equals 1, so let's just call this that there. And x equals 0, that. Revolve that around the y-axis. So it would form something like this little kind of funnel type shape, right? Now your r is the distance between the curve in terms of y, so that you're going horizontally, so y squared. Technically it's minus 0. And then the volume would be pi times the integral from, in terms of y, we're going from 0 to 1 of y squared squared dy. And again, we can go ahead and integrate that, but it's not the actual integration that I'm worried about. Okay, so let's move on to the washer method, still using the square root of x graph. Okay, so find the volume of the solid formed by revolving square root of x, y equals 1, and x equals 0 about the x-axis. So that's the graph that we just talked about, square root of x, y equals 1, x equals 0. So this piece right here, revolve it around the x-axis. Okay, so that's weird, right? Because if you were to do that, I'm just going to try to copy my little mirror image shape here. I'd have this. So when I revolve that, there's this big open space. You can kind of think of it as like a bowl. It's got a cylinder on the outside. It's got a cylinder on the outside, and it has this hollowed out space in the middle. So the reason we call this a washer method is because a washer is like one of those little metal donut looking things, right? It's got a hole in the middle. It has absent space. So we're going to be interested in looking at R, capital R. Capital R is the outer radius. And we're also interested in looking at lowercase r, which is the inner radius, the negative space. And if I think about this, if I find the volume of the outer, if I find the volume of the big cylinder, and I scoop out or subtract out the volume of this kind of dome on the inside, then I will be left with the net volume of the overall thing. So the volume is equal to the outer volume minus the inner volume. Okay, in this particular problem, the outer volume is pi r squared minus the inner volume is pi lowercase r squared. You have all those little disks, and you're adding up a bunch of them from x equals 0 to x equals 1. Oh, and how do I know it's x equals 0 to x equals 1? And what am I looking at here? Sorry, my representative rectangle, we're rotating around the x-axis, right? So my representative rectangle is vertical. It needs to be in terms of x. Even though the space we were looking at started out kind of in terms of like a y equals 1. Okay, so the volume is equal to, let's do the outer volume first. Pi times the integral from 0 to 1. What is the outer radius? Well, the outer radius is 1 no matter what, whether you're over here at 0 or heading across over to 1, it is fixed. It's the volume of a cylinder. So it is just the integral from 0 to 1 of 1 squared dx. We're going to subtract from that pi times the integral from 0 to 1 of, what's this inner part? Well, this little inner representative rectangle is still in terms of x, but that's where you're actually hitting the square root of x graph. The height of that piece is square root of x, and then you're subtracting from it 0. So that is square root of x squared dx. All right, so if we want to integrate this one, eventually I'm going to hop to my calculator to do each of these, but the integral of 1 is x from 1 to 0, 0 to 1. And then here, this is just x, so you're getting x squared over 2. So this is going to be 1 times pi minus pi times 0, so pi minus pi over 2 minus 0. Pi minus pi over 2 is a volume of pi over 2. I always set up the integral for this part, but yes, this is just the volume of that cylinder, which has a height of 1 and a radius of 1. So pi r squared times height. Pi times 1 squared times 1 still gets you that. So I would just set it up the calculus way, but you can also just use geometry for that first part. All right, let's look at another example. So we've got the region square root of x, y equals 0, x equals 4. We're just going to set all of these up, by the way, because again, we can integrate by hand or with our calculator fairly easily at this point, hopefully. The hard part is sketching the graph and making sure you have your r and your r set up correctly. All right, so some of these will be disk, some will be washer. So square root of x looks like this. If x equals 4, y equals 2. Y equals 0 is this section here. So here's our area that we're looking at. We want to rotate it about the line x equals 4. So we want to send it around this thing, which means it's going to make a dome shape over here. Your representative rectangle looks like this. Okay, I don't have a capital R and a little r. There is no negative space in this one. It's just a dome. So there's just a capital R. Capital R is equal to, think about what we have here. It's a horizontal rectangle. So I don't want to have square root of x. I want to make this y squared equals x. I need everything to be in terms of y. So what is this little r? Well, on the right side, I've got 4, and then on the left side, I've got the y squared curve. I don't want to do y squared minus 4 because y squared is this little distance right here. 4 is the distance from the y-axis all the way out to here. So what I want to do is always think kind of right minus left. So 4 minus y squared. And let's go back to the other horizontal one we did. Oh, sorry, that was on a previous day's notes. Let's see. But yeah, back here. Here, when I did the 2 minus y squared minus negative 3, that was because 2 minus y squared is on the right and negative 3 is on the left. So when you're coming up with this r for a horizontal, it's right minus left. When you're coming up with r for vertical, it's top minus bottom. I should have said that yesterday. Hopefully I did if we were in class. All right. So there's capital R, and then the volume is going to be pi times the integral. We're in terms of y now, because we're going sideways. So 0 to 2. of 4 minus y squared dy. All right, so we're not going to solve. We're just going to set these up. Now take the same region and go about the line x equals 6. So for this one, I'm going to scooch my graph over and sketch it again. We had our square root of x graph. At 4, we were at 2. Okay, but we're not rotating around 4. We're rotating around 6. So we have this like little axis of symmetry here. If we reflect this across that line, you get this shape. And then you're going to be rotating it around. So you're going to get this like cylinder hole in the middle. But then you're also going to have this huge dome shape on the outside. So it's like a dome with a drilled cylinder going through the center. So you do have a little r and you have a big R. I'm sorry if let me get some of my circles out of the way here. It's a good idea to draw your R's connecting the original curve so you don't subtract the wrong way. Okay, so little r is fixed. It is always the distance between 4 and 6. It's 2 units. 6 minus 4 is 2. Capital R, right minus left, is 6 minus the quantity y, oh wait, not a quantity, sorry, minus just y squared. Because we're going right minus left, and the left side that I hit there is the y squared curve. Okay? And then my volume is equal to pi times the integral from 0 to, now we don't have to figure out when we hit 6, because remember the top of this curve is when y is 2. It doesn't reach any higher than that. So 0 to 2 of 6 minus y squared dy. That's my outer piece, right? Minus pi times the integral of 0 to 2 of 2 squared dy. Now you can set it up like this, or you might notice like these both have pi integral from 0 to 2. You can merge those together. It is the same as pi times the integral from 0 to 2 of 6 minus y squared minus 4 dy. So you are allowed to put those together. I would just be careful about that, that you don't forget to square something, or that you don't subtract the 4 and then square the whole thing. All right, y equals square root of x, y equals x squared, rotate about the x-axis. So let's sketch the graph first. Square root of x, something like that. X squared, something like that. Probably need to know where they meet, right? Obviously 0, 0. This point right here is 1, 1. And if that weren't obvious, then we would have to solve it algebraically, set them equal to each other. We're taking this region and we're rotating it about the x-axis. So I always draw just the reflection like that. And then I try to visualize like, okay, what is it going to be? So it's going to be this sort of bowl type shape, and then it has sort of a funnel kind of cut out of it. If you don't want to draw the 3D piece, all you need to remember are the big rectangle, what's the outer R, and what is the inner R. The outer R is the curve that's on top, which is the square root of x graph, minus the axis of symmetry or rotation, which is 0. The little r, it's not fixed, it's changing too, it's x squared minus that little axis, which is 0. Okay, and then the volume is pi times the integral from 0 to 1 of, if we put these together into 1, it's big R squared minus little r squared dy. Now, of course, you could simplify that. Yes, that is just x minus x to the 4th. Totally fine. I'm just kind of doing this for the notes. Okay. Oops. scrolled too far. So for example 3, let's sketch this region. X squared plus 1. It's a parabola with a vertex at 1. Y equals 0. That's just the x-axis. X equals 0, y-axis. And x equals 1. So we're at 1, and then 1 would be 1, 2. So now we're talking about this region, rotated about the y-axis, this way. When you do that, you're getting one of those cylinders with like a little bowl cut out of it. Okay, so let's see. We're rotating sideways. So our rectangle of rotation on the outer part, big R, is going sideways. I can see that big R is fixed all the way across. It's 1. What about little r? Little r going sideways needs to be in terms of y. It's connected to the x squared plus 1 graph, but I need to solve that for y. So x squared plus 1, square root of y minus 1 equals x. I don't have the plus or minus because think about this original curve. The original x values on this side were positive. Those are the ones I'm rotating around. So I don't want to have plus or minus because I'm not looking at the whole piece. I'm looking at just this section here. So that's why it's just positive square root of y minus 1. So that means that little r is square root of y minus 1. And sorry, both of them would technically be minus 0 because they're connecting back to the y-axis. All right, so the volume is pi times the integral from, we're talking about y values, 0 to 2, of big R squared, which is 1, minus little r squared. Squaring the square root would just be y minus 1. That is in parentheses, though, because you're subtracting it. Or if you think you might mess that up, split it into 2 different integrals. Oh, wait. I just about messed that up. Sorry, I can't put it into 1. I could put it into 1 if this bowl dipped all the way down, but that little r doesn't go from 0 to 1. Adjustment here. Goodness gracious. It doesn't go from 0 to 2. It goes from 1 to 2. So we did need to make that adjustment. You can only merge into, that's why I usually separate it so I don't mess things up like that. Up until now, all of the bounds, limits of integration have been the same, but here they're actually not. Okay, number 4. This picture is a bit strange, but so let's try to think of what we're looking at. A manufacturer drills a hole through the center of a metal sphere. It's supposed to be a sphere of radius 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? So, okay, let's just look at this. If you have a sphere, then you rotate it a circle, right? If we had our original equation was a circle, we could rotate that around an axis and we would have a sphere. Okay, so because normally we're given an equation and in this one we're not. What is the equation of a circle? The equation of a circle is x squared plus y squared, and it equals r squared. We're told the radius of the sphere is supposed to be 5 inches, so it equals 25. All right, now if I'm looking at this, let's just go in this first quadrant here. The sphere would have an outer r, an outer radius, and the sphere would have an inner radius. Even though the top of the sphere here has this radius of 5, right? We're looking at once we rotate it, what is the different distance, not from the circle, not from the outer side of the sphere to its center, from the outside of the sphere to that, say, x-axis. That's going to be different than connecting back to the center. So it's not fixed at 5 is what I'm trying to say. Well, let's just say we're rotating it around the x-axis. So if I want things to be vertical, I need to solve my circle equation for y. so that I can get it in terms of x. And again, I'm talking first quadrant, so I chose a positive square root. So that big R is square root of 25 minus x squared. Now little r is fixed. We have a hole with a radius of 3 inches. So it is 3 no matter what. That doesn't vary throughout the sphere. And so then the volume should be pi times the integral. What are the bounds here? I have to think about if I know like where does this outside circle meet the 3-inch hole? So if I know that y is 3, what is x? X squared plus 3 squared equals r squared. X squared is 16. So x is 4 inches right here where we drilled this hole. Because remember, you drill a hole through a sphere, you're kind of cutting off the ends of it, right? It doesn't have a rounded end anymore. We're trying to figure out where does that cut off. On the other side, it would be -4. So we're going from -4 to 4 of big R squared, so 25 minus x squared. When I square the square root, it's gone. Minus 3 squared minus 9 dx. And then again, we can integrate that either by hand or with our calculator. That picture is a bit strange. You would have a better picture if it were an actual AP problem, and they would indicate that you're needing to rotate a circle. So we kind of left that one a bit open for our notes. All right, that's it for today.